आज मतलब हम लोग क्लास 11 फिजिक्स रिवीजन करेंगे, फर्स्ट बुक का रिवीजन करेंगे। तो यहाँ पर हमारा जो है पहला चैप्टर है मोशन इन ए स्ट्रेट लाइन। तो मोशन इन ए स्ट्रेट लाइन, इसको रेक्टिलिनियर मोशन कहा जाता है। मतलब स्ट्रेट लाइन मोशन, हमारा जो टॉपिक होगा वो रेक्टिलिनियर मोशन के साथ रहेगा। तो ये रेक्टिलिनियर मोशन के साथ आपको जैसे डिस्टेंस आता है, डिस्प्लेसमेंट आता है। तो इन रेक्टिलिनियर मोशन वी गेट डिस्टेंस, डिस्प्लेसमेंट, and then speed, velocity, acceleration, retardation. All these things comes under the motion in a straight line. So here in motion in a straight line, distance, this all you have learned, and I am just doing the revision, the first book revision for class 11. Distance, it is the total distance covered by a body here, but displacement, it is the shortest distance, that is the distance between the initial and the final point. It is the distance between the initial and the final point, whereas distance, it is the total path length, that is the total distance covered, that is called distance. Total path length, where displacement, it is the distance between the initial and the final point. So there is a difference between distance and displacement. Similarly, we come to speed. So speed, it is, the definition is distance by time, where velocity, its definition is displacement by time. Now the main factor is that it is rather difficult to get any body which is in constant velocity or in constant speed. This is a theoretical part, that there is a constant speed or constant velocity. It becomes rather difficult to get constant speed or constant acceleration, but it is easy to get constant acceleration, because a free falling body, it has constant acceleration, that you all know. So here, since the speed is not constant, we go for average speed. The average speed, it is the total distance covered by total time taken. Therefore we go for average speed. And similarly, we go for average velocity, that is the x2 minus x1 by t2 minus t1. Here velocity average velocity becomes easy to describe if we take the coordinate system. In coordinate system, it becomes easy to describe average velocity. So initially, if we take xy plane, and x axis as time and y axis as position, so at xt, that means at t1 your position was x1, and at t2 your position was x2. So x2 minus x1 by t2 minus t1, this gives the average velocity. According to the convenience, it has been to describe velocity, we express it in coordinate system. Now acceleration, that you know, acceleration, it is a change in velocity divided by time, that is v minus u by t. Means initially a body was in velocity u, and after time t its velocity became v. So during this time t there was change in velocity v minus u, so your acceleration is equal to v minus u by t. Here acceleration, we can get constant acceleration. This is possible, but constant velocity and constant acceleration is practically little bit difficult. So the formula related to constant acceleration, when the acceleration is constant, we can apply these formulas, that is v is equal to u plus at, s is equal to ut plus half at square, v square is equal to u square plus 2as. These are the formulas you can apply if it is in constant velocity, if it is in constant acceleration. So this is all about your motion in a straight line. Now we move to the motion in a plane. So motion in a plane, here before starting motion in a plane, let me tell one more thing, that distance and speed distance and speed, they are considered as a scalar quantity, where displacement, velocity and acceleration, they are considered as a vector quantity. So there are different types of graph, there are different types of relations between distance and time, uh, displacement and time, velocity and time. And one more important thing is that in velocity time graph, the area under the velocity time graph, we get displacement. This is an important point. And if they are in, suppose your in displacement time graph, if your velocity is if your velocity is uniform velocity, then in displacement time graph you will get a straight line. You will get a straight line. So there are different graphs related to displacement time, velocity time. In velocity time graph, the area under the velocity time graph, you get the displacement. The area under the velocity time graph, you get the displacement. So this is all about your motion in a straight line. And uh, uh, and all these formulas are all these formulas, by the help of these formulas, you can solve the problem. The only important point is that while when you are reading the problem, you pay attention that whether it speaks constant acceleration or constant velocity or constant speed or average uh, velocity, average speed. Suppose if the question in the question, if the body is moving with a constant speed, then you can use the formula distance is equal to speed is equal to distance by time. And uh, if it is in uh, the body is moving with a constant velocity, then you can use the formula displacement by time. But in the question, if it is in your problem sum, if you uh, try to if you while reading the problem sum, if you find that the body is moving with the constant acceleration, then you can use any of these three formula: v is equal to u plus at, s is equal to ut plus half at square, v square is equal to u square plus 2as, any of these formulas depending upon the data given to you. And another important point you must remember: when a body is falling freely, acceleration is constant, that is acceleration due to gravity. This is an important point. That means whether you uh, throw the ball upward or the ball moves downward, here the only acceleration is the acceleration due to gravity, and this acceleration due to gravity is constant is constant. So this is an important point you must remember. Now we move to the motion in a plane. In motion in a plane, that is earlier it was a straight line motion, rectilinear motion, one dimensional, and now motion in a plane, that means it is in xy plane. This is an xy plane. So to represent a motion, vector has been used, and the properties of vectors has been used to explain the motion in a plane. And the most important point here is that the a vector in a plane, the most important point here is that uh, in an xy plane, any if you take any point in an xy plane, and if you join that point with the origin, you take any point in the xy plane in, and if you join that point with the origin, then it is called a position vector, and its direction will be always outward. That is, its direction will be from O to P. This is the position vector. And there are two laws of additions of any two vectors, that is the triangle law and the parallelogram law. And by the help of the triangle law and the uh, parallelogram law, you can add any two vectors, and you can also find the magnitude of the sum of any two vectors. That means sum of any two vectors will give you the resultant vector, and you can find the direction as well as magnitude of the resultant vector. If the two vectors are in right angles, then your resultant vector, magnitude of the resultant vector, can be calculated by the Pythagoras theorem. Now another important point is that this vector is brought under coordinate system. So where I told you that any point in the plane xy plane, any point in the xy plane, and that point, if you join with the origin, then it becomes the position vector, and it is always directed outward. The point P, as you know, in xy plane, the point P, it will have some coordinate. That is, let us take it is 2 comma 3, the coordinate of point P in xy plane be 2 comma 3. That means 2 comma 3, that is, you moved 2 units along x-axis, and then you moved 3 units along y-axis. So the resultant vector will be your OP vector. OP vector. So when I told that the point P has the coordinate of point P is 2 comma 3, that means we moved 2 units along x-axis and 3 units along y-axis. So we moved 2 units along x-axis. So the x-axis, the direction of the x-axis is given by a unit vector called I cap, and the direction of y-axis, that is, it is given by a unit vector j cap. So your resultant vector OP vector will be 2I cap plus 3j cap. So this is how a vector is represented in a two-dimensional plane. If we go further, that is in three-dimensional plane, your z-axis will come into existence. So your OP vector will be equal to, suppose the in your three-dimensional plane, you take a point P and its coordinate be, let its coordinate be 2 comma 3 comma 4, then your OP vector, that is the resultant vector, that is the position vector, that will be equal to 2I cap plus 3j cap plus 4k cap. So this will be the resultant vector OP vector, or you can say this is the position vector. So if a vector is given to you, let a vector, it is given to you, that is it is 2 I cap plus 3 j cap. That means the point, coordinate point, the point on the xy plane is 2 comma 3. This this is a small nutshell about your vectors which is used in this motion in a plane. So motion in a plane, what is the most important factor is that why you used a vector, because any vector in a plane, any vector in a plane, it can be resolved into two parts, that is along x-axis and along y-axis. That means any vector in an xy plane has two components, any except the vector which is parallel to x-axis or y-axis, except the vector which is parallel to x-axis or y-axis. Any vector, it has two components, one along the x-axis and another along the y-axis. What does this actually means? That is, let us take a vector that is OP vector, and it is making an angle theta with the x-axis, means we are considering a two-dimensional plane. We are considering a two-dimensional plane, and an OP vector, that is OP vector, is makes an angle theta with the x-axis. OP is your position vector and it makes an angle theta with the x-axis. So the component of OP vector along the x-axis is OP cos theta, and along y-axis it is OP sin theta. That means this is the scalar quantity OP cos theta. Remember, when you write cos theta or sin theta, it becomes a scalar component. So the OP vector along x-axis, its scalar component is OP cos theta, and along y-axis it is OP sin theta. So you can also write that OP vector is equal to OP cos theta I cap plus OP sin theta j cap. This you can write it like this. What does this actually means component? Let us take about the force. That means if a force is acting on a body and with along x-axis, it is making an angle 60 degree. So that force has two components, one along x-axis and another along y-axis. That means there are two effect of force of that uh, force F. It has two effect. One is along the x-axis and another is along the y-axis. So in this chapter, it is we start with the projectile motion. What is a projectile motion? That means when a body is projected upward, that is, we have considered this in an xy plane, and up in a projectile motion, a body of, say, uh, a body is projected at an angle theta with the x-axis. So when a body is projected uh, along at an angle theta, uh, when a body is projected upward, which is making an angle theta with the x-axis, so this velocity uh, can be resolved into two parts. One is along the x-axis, that is the horizontal component, and it will be u cos theta, and another will be the along y-axis, that is the vertical component, that is u sin theta. So here you see that you have projected a body which is make with a velocity u. You have projected a body, that means it may be a stone or something else, a body you have projected it upward, which is making an angle theta with the x-axis. So and you have projected it with velocity u. So this can be resolved into two parts. One is along the x-axis and other is along the y-axis. So that means along the x-axis it will be u cos theta I cap, and along the y-axis it will be u sine theta j cap. So the u cos theta, which is the horizontal component, and since the gravity is working perpendicular to the displacement, you're perpendicular to the displacement, so no work is done. And as there is no work is done, so uh, the velocity remains no, means there is no external force, that means no work is done, that means no external force. And when you know that when there is no external force, the body moves with uniform velocity. So your horizontal component, the velocity which is in the horizontal component, will remain constant. But the velocity in the vertical component, the velocity in the vertical component, here there is the effect of gravity, and because of the effect of gravity, as the body moves upward, its velocity decreases, and we come to a point, to a height where your velocity, that is your vertical component of the velocity, is zero. But remember that at the point where your vertical component of the velocity is zero, but your horizontal component, that is u cos theta, still exists, and it is a constant. So what happens, that is the u cos theta, this velocity components makes the stone to move in the forward direction, and v sin theta, it makes to move the body in upward direction, giving you the shape of a parabola. So by the help of which, there are some of the factors which are formulas has been derived. So the formulas are such as your horizontal range, that is the maximum displacement in the horizontal direction, your time of flight, and time of flight, uh, such that these are the formulas which has been tried derived. Time of flight, that is the total time taken by the projectile when it is projected, and the time when it reaches the ground, the total time. Now the next important point here is that you must remember the time taken by the body to move to the highest point, and the time taken by the body to decline from the highest point to the ground is the same. So as they have derived the time of flight, the formulas they have derived, that is twice your initial velocity into sine theta, divided by g. The time of flight, that is equal to twice your initial velocity, that is into sine theta, that means your vertical component of your velocity, divided by g. This is the time of flight. Similarly, the horizontal range, that is the maximum distance which the body moves in the horizontal direction, that is your initial velocity square sine theta 2 theta by g. That means it is a range, that is the horizontal range, it is your initial velocity square into sine 2 theta by g. So theta, it is the angle which the projectile makes it along with the x-axis, and u naught, it is the initial velocity with which it is projected. So these are the formulas. And again, one more thing important came here in the class 11, that is the first of all, it is difficult to get a constant velocity. So uh, so what happened, that is we know that the velocity, it is average velocity, that is x2 minus x1 by t2 minus t1. We know that this is average velocity. So your average velocity, that is equal to x2 minus x1 by t2 minus t1, that is delta x by delta t. Now, if we take limit delta t tends to 0, then this your average velocity is gets converted into instantaneous velocity. Your average velocity gets converted into instantaneous velocity, that is dx by dt. So the instantaneous velocity, it is that at a given instant what will be the velocity of the body. So similarly, uh, uh, we uh, we get instantaneous acceleration, that is the average acceleration, that is v2 minus v1 by t2 minus t1. So your average acceleration will be equal to again dv by this average acceleration is converted into instantaneous acceleration, that is dv by dt. So this is uh, in this topic motion in a plane. And the next important is when a body is moving in a circular path. So when a body is moving in a circular path, that means its speed can be uniform. That means you can say the body is moving with a uniform speed, but your velocity is not constant, because at every instant the direction of the velocity changes, because the direction of the velocity at any point is given by the tangent. So at any point the direction of the tangent changes, so your velocity, there is change in velocity, and as there is change in velocity, there is change in acceleration. So when a body is moving in a circular path, there is an acceleration is produced, and the acceleration which is produced, it is directed towards the center of the circle, and so it is called as centripetal acceleration, and this acceleration is equal to v square by r. This centripetal acceleration is equal to v square by r, and which is directed towards the center of the circle. Now here again there is a relation between the linear velocity and angular velocity. Angular velocity, it is expressed in terms of theta, that is your angular velocity is theta by t, uh, it is theta by t, and your linear velocity is displacement by time. So there is a relation when a body is moving in a circular path. So there is a relation between the linear velocity and angular velocity. Your linear velocity v is equal to r omega. So this is all about your motion in a plane, which is given in your book. And now my next topic goes to the laws of motion. So here you say laws of motion. This came from the fact that earlier it was a conception that whenever a motion is required, an external force is required. When there is a motion, an external force is required. But this Galileo proved that there is no need of external force for a body to be in motion. And he proved that when there is no external force acting on a body, the body is moving in uniform motion. That means when your external force is equal to the frictional force, that means when your external force is equal to the frictional force, that means no force is acting on the body, and the body moves with uniform velocity, that means it moves with constant velocity. Taking the concept of this Galileo, Newton introduced the first law of motion, which is also known as the law of inertia. And this law of motion, which is also known as law of inertia, that is every body, either it is in rest or in motion, it has the tendency to remain. Suppose a body, that is inertia of rest. If a body wants to be in rest, if a body is in rest, it will always remain in rest unless and until it is acted upon by an unbalanced force. Means if a body is in rest, it will always remains in rest. It is the tendency of the body to remain at rest unless and until an external force act on it. So when an external force act on it, then only the body will move. Similarly, inertia of motion, that is, if a body is in motion, it will always remain in motion unless and until acted upon by an external force. So to explain the inertia of rest, uh, the book has given some examples. In the book, it has given some example. Suppose inertia of rest, you take a glass, and on the glass you placed a cardboard, and in the middle of the cardboard you place a 1 rupee coin. When you strike the cardboard, you strike the cardboard parallel to the ground. In a one stroke, you must strike it in a one stroke parallel to the ground. Then your card will move out, but the coin will fall into the glass. This is because inertia of rest, because the coin is in inertia, or it is in the rest condition. It has the tendency to remain in rest. Similarly, the most practical phenomenon which you have seen, that in you what you do is that your mattresses or your the any cloth, if you have to remove the dust, if you have to remove this dust, you just hang it on, you just hang it, and then you strike it with a stick. What happens when you strike that cloth with the stick, with a stick, then the cloth changes its position, but since the dust particle is at rest, it falls downward. So this is how the dust particles gets removed from the cloth. There are also given about the uh, about examples of inertia of motion in your book. That is, when a person sitting in a bus is in motion, and when brakes are applied, the upper part of the body moves forward. These are the examples of inertia of motion. Now here we this is about first law of motion. The first law of motion is also called the law of inertia. Now next we move to the second law of motion. So before explaining the second law of motion, there a term has been introduced, that is momentum. What is momentum? Momentum, it is mass into velocity. That means mass into velocity, that in order, suppose a bullet strikes a wall and it makes a hole in the wall. So in order to explain the reason how the bullet was able to make a hole in the wall, to explain it, it is possible by the help of momentum, that is mass into velocity. So the effect, that what is the effect when a bullet strikes a wall, the effect, it is that it made a hole. This is because, not only because of velocity alone, but mass alone, but it is because of the product of mass and velocity. So a term change in term momentum came into existence. Now, the second law of motion states that the rate of change of momentum of a body is equal to is proportional to the external applied force. That is, the rate of change of momentum of a body is equal to the external force. So here your F is proportional to dp by dt, and F, that is equal to K, this is a proportionality constant, dp by dt. So change in momentum, that is mv minus mu by t. And so this is change in momentum. So v minus u by t, this gives acceleration. So F is equal to K into ma. And now if a body of mass 1 kg moving with an acceleration 1 meter per second square, then the force acting on it is 1 Newton, then the value of K comes to 1, and so F is equal to ma. This is the result we obtain from the second law of motion. And to explain, that is the one more important factor, that is F is equal to ma, and another formula, that is F is equal to F is equal to ma, that is mv minus u by t. Here we see that t is inversely proportional to, means F is inversely proportional to t. That means if your time increases, the force decreases. This is the condition when a cricketer, when it catches a ball, it shifts its hand backward. It shifts its hand backward. That means it increases the time so that the impact of the ball on his hand is minimum. So this is according to Newton's second law. Now your Newton's third law states that to every action there is equal and opposite reaction. And this Newton's third law is very important, because this Newton's third law, according to this, to every action there is equal and opposite reaction, and this helps to state that your momentum is conserved. To every action there is equal and opposite reaction. This Newton's third law helps you to state that your momentum is conserved, that is, momentum before collision is equal to momentum after collision. And now our topic moves to the friction, that is the which is the last topic, that is the in this chapter. Here, friction, first of all, I would like to tell that friction, it is not a conservative force, it depends on path. So here, friction, that is the force which opposes the motion of the body, and this friction, always act at the contact surface between the two bodies. That means if the surface is rough, your friction will be more, and if your surface is smooth, your friction will be less. Now, there are two types of friction. One is the static friction, and another is the kinetic friction. Static, its words is itself explains it, that when a body is at rest, when you apply an external force, yeah, the body does not move. That means your external force is equal to the frictional force, so the body does not move. You slowly increase your external force, and the frictional force will also increase in the same amount, and at a point, you will reach to a point where the frictional force does not increases, and if you increase your external force, the body will start to slide. So that point, that is the maximum point where the body frictional force, the maximum point where the friction acts where acts, and the body does not move at to that maximum point, it is called the static friction. And you remember that the most important thing is the frictional force. It is depends on the normal reaction, that is the you can say indirectly the weight of the body. That means the weight of the body, it acts downward, and its normal reaction, that is perpendicular to the surface, it acts upward, and the normal reaction is always equal to your weight of the body. So your friction force, it depends on the normal reaction, and frictional force, that is equal to mu uh, into normal constant, that is called coefficient of friction, and that is uh, uh, frictional force, that is static frictional force, that is equal to coefficient of friction into normal reaction. That That means you find that your frictional force, it depends on the weight of the body. This is very important. And when the body starts sliding, then that friction is called sliding friction, and your sliding friction is always less than the static friction. That means your kinetic friction is always less than the static friction. This is, you may find it that when a car is at rest, then when you move the steering, it requires, in order to turn your wheel, it requires more force. But when a car is moving, to turn the wheels, uh, you, a slight movement in the steering, you can move the wheel. So here you see that your static friction, kinetic friction is less than the static friction. So this is all about, and in this you will get the board car moving in a circular path, the car moving in a circular path and in a banked road. You remember the most important point here, that when a car, you must remember, that is when a car is moving in a circular path, the frictional force, it acts as, which is directed towards the center of the circle. You must remember that is the frictional force, it is directed towards the center of the circle. You must remember that this is very important, that when a body is moving in a, when a body is moving in a circular path, then your frictional force will act towards the center of the circle, and that frictional force is it act as a centripetal force, and so your frictional force will be equal to mv square by r. Remember this, this is the very important point. When a body moves in a circular path, your frictional force will be directed towards the uh, center of the circle, and this frictional force act as a centripetal force. Now next, in a bank road there are two effects, that is frictional force and the normal force. The component of frictional force, that means the component of when a body is moving, that is car, when a car is moving in a bank road and it is performing a circular motion in a bank road, then your centripetal acceleration, the component of the normal of the car and the component of the frictional force, they together constitutes the centripetal force. Remember this, that is the frictional force, because the frictional force will act along the inclined plane, the frictional force will act along the inclined plane, and the normal reaction, that is of the body, will act perpendicular to the contact surface. So the component of the frictional force and the component of the normal reaction, they together constitutes the centripetal force. So it comes something like this, that is n cos theta plus f n sin theta, normal reaction n sin theta plus f cos theta, they together constitute the normal, consider the centripetal force, and theta, it is the angle which is the bank road makes with the horizontal, with the horizontal surface. So this is all about your laws of motion in your chapter laws of motion. Now let us move to work, energy and power. So here your work, energy and power. So work, again a vector, it has been explained by the help of work vector, because work done, it is the dot product of force and displacement. It is the dot product of force and displacement. So its magnitude is magnitude of s into dot magnitude of displacement, in dot cos theta, where theta is the angle between the force and displacement. So here this is a simple work done, and so from this formula W is equal to uh, work done is equal to F d cos theta. From this formula we see that there are the three factors, which constitutes the work done. One is the force, other is the displacement, and another is the 3. There are three factors. If your force is 0, no work done. If your displacement is 0, no work done. If your angle is 90 degree, no work done. So remember from this, that is work done, it depends on force, displacement and theta. If your force is 0, no work done. If your displacement is 0, no work done. And if the angle between force and displacement is 90 degree, no work done. So a work done depends on force, displacement and theta. Now in this book it has been given that about vectors dot product. So in dot product we actually do the multiplication of I, J and K. In dot product we do the multiplication of I, J and K. Why? Because I into I, the angle between them will be cos 0, so its value is 1. J into J, angle between them is they are unit vectors, so angle between them is 0. So your value comes out 1, and K cap into K cap, its value comes out into 1. But I dot J, because the angle between them is 90 degrees, so its answer is 0. So in dot product we do I into I dot I, J dot J and K dot K. So here this is all about dot product, it is given here. Now here a most important theorem it has been given, that is the work energy theorem. Why work energy? That means work. When is work done? That means there must be an external force, and when there is an external force there must be a displacement. So here you see that the work done is equal to change in kinetic energy, because it is little bit different from the conservation of energy, little bit, because in the conservation of energy, that is when the kinetic energy is conserved, that means at that case there must be no external force. Remember this very important point, that is when energy is conserved, that is in kinetic energy, if the your kinetic energy is conserved, that means when this takes place in elastic collision, your kinetic energy is conserved. So in such cases when there is no external force, then only if your collision is elastic collision, then your kinetic energy is conserved. But in inelastic collision, the kinetic energy is not conserved, there is loss in kinetic energy. So it is little bit different here. When kinetic energy is conserved, that means you will find it later on, which I will explain, that your mechanical energy is conserved. That means your kinetic energy is converted into potential energy. Here we have taken the example of a free fall ball, that means there is no external force. So here your kinetic energy gets converted totally into potential energy. But this is a case when there is an external force acting on a body. So the work done by an external force, that is equal to the change in kinetic energy, and this is a very important theorem, and which this can be derived, this can be easily derived, that is there is nothing difficult. This can be easily derived by taking the formula V square is equal to U square plus 2as, by taking the formula this, and if you multiply it by half m both sides, then you get that K final minus K initial is equal to work done, that is F dot d displacement. You get this formula. Now here in this another is that kinetic energy, and the kinetic energy uh, that is it is the energy possessed by the body due to the motion. This is the energy this is the energy possessed by a body due to the motion of the body, and due to the motion of the body, and it is equal to half mv square. Now we come to the force there, because we are discussing both theoretical as well as practical. The force may be variable force, so work done by variable force can also be calculated. That is, if you work done by variable force also can be calculated. That is, we take a two-dimensional plane, that is x and y. The x-axis represents the position, that is the displacement, and y-axis represents the force, that means force is a function of x. So the area under this curve, the area under the curve will give you the work done, and this can be calculated by the help of integration. So similarly, the work done can be variable forces work energy theorem. That means it wants to tell you that work energy theorem can also be is also applicable to variable forces, and this is also applicable to variable forces, and this can be derived by the help of calculus, that is integration, that is kf minus ki, k final minus ki is equal to work done. Now we move to the potential energy. The potential, about potential energy, the details in potential energy I have discussed in my earlier video, that is what is potential energy. Now today I am going to give you in the nutshell, that is the potential energy, that is it is due to the energy gain due to the position, and it is equal to mgh, that is the potential energy of a body. That means if a body is lying on your floor and you lift the body and move and keep it on the table, that means the work done by your external force is stored in the form of potential energy in the body when it is placed on the table. So here potential energy is equal to mgh. Now next is the conservation of mechanical energy. Your mechanical energy, that is equal to kinetic energy plus potential energy. So here you see that your kinetic energy, that is your kinetic energy is equal to the potential energy, or sum of the kinetic energy plus potential energy is conserved, that is constant. This is explained in your book by the help of a ball falling freely from a height h, and it has been divided into three sections, that is A at the top when the body is released, and B an intermediate point, and C a point just before it touching the floor, or just before touching the floor. So at these 3 points, when we find out the kinetic energy plus potential energy, we get the value is constant, and that is equal to mgh. At point A, you get kinetic energy plus potential energy is equal to mgh. At point B also you get kinetic energy plus potential energy is equal to mgh, and at point C also you get kinetic energy plus potential energy is equal to mgh. So your mechanical energy is conserved. Now the next important point here is the spring force. That means in potential and in the spring there is potential energy. So let us consider a spring in its normal position, and at that normal position the end is considered in coordinate system. Let the end one end of it be attached to a wall, and the other end is free and in the normal position. When it is not in a stretched or in a compressed position, that is called the normal position. And in the normal position, let the free end of the spring be represented at x is equal to 0. Now when you pull the spring in the positive direction of x-axis, a force is developed inside the spring which resists the motion of the displacement, that which resists the displacement. That force is called the spring force, and it always acts in opposite direction to the displacement. So according to Hooke's law, this spring force is proportional to the displacement. So Fs is proportional to x displacement. So Fs is spring force, that is equal to some constant minus k into x. Why minus is considered? Because the direction of the spring force is opposite to the direction of the displacement. Now because here, as I have told you earlier video, when there is work done against an existing force, the energy stored is the potential energy. So here also the energy stored in the spring is the potential energy, and that potential energy is equal to kx square by m. That's potential energy. That means the work done, if you consider the work done by the spring force, then it will be minus kx square by 2. It will be minus kx square by 2. That is the work done by the work done by the spring force, and this is the potential energy. So here it is about the spring force. And now when Fs is proportional to displacement, your Fs is spring force is equal to minus k into x. If your spring if your k is large, that means the spring is stiff, and if your k is small, that means the spring is soft. So here you see that because there is energy, so when there comes energy, so here the theory of collision also come into existence, that when two body collides, so there are elastic collision and completely inelastic collision, and intermediate between the elastic and completely inelastic collision. In the elastic collision, when the two body collides, it after collision it regains its original shape. So it regains its original shape. In elastic collision, the kinetic energy before collision is equal to the kinetic energy after collision, but at the time of collision your kinetic energy is not constant, but kinetic energy before collision is equal to kinetic energy after collision, and similarly your momentum before collision is equal to momentum after collision in elastic collision. But in completely inelastic collision, what happens after when the two body collides, and after collisions the two body moves together. So the two body moves together. So here there is momentum is conserved, that is momentum before collision is equal to the momentum after collision, but here your kinetic energy is not conserved, there is loss in kinetic energy. So these are the important points which you must remember. And in elastic collision, you know that the momentum is conserved, that the momentum before collision is equal to the momentum after collision. So here your final velocity of, let us consider two bodies m1 and m2. So two bodies m1 and m2, and m1 is moving with a velocity u1, and m2 is moving with a velocity u2. They are the initial velocity, and after collision let the velocity of m1 be v1f, and the velocity of body 2 will let it be v2f. So here they have calculated it by taking the conservation of momentum or conservation of kinetic energy, they have calculated it, that is V1F, that is the final velocity of the body of mass m1. The final velocity is equal to m1 minus m2 divided by m1 plus m2 into vi, v1, the v1I, that means initial velocity u1, that is your initial velocity u1 of the body of mass m1, and your final velocity of body 2 m2, that is 2 m1 by m1 plus m2 into u1I, that is means u initial velocity of body 1. So here for elastic collision they have given you the final velocity of body of mass m1 and the final velocity of body of mass m2, and they have derived the formula, and they have derived these two formula. And the one of the most important thing is that in this collision, if the two bodies are of same mass, then let the second body be at rest and the first body, they are of same mass. So when let the second body be at rest, when the first body moving with velocity u, say first body moving with velocity u strikes the second body which is at rest, what happens? The first body comes to the rest and the second body moves with the velocity u, and the second body moves with the velocity u. See, this is an interesting fact, that when the two bodies are of same mass, let the second body be at rest and the first body moving with velocity u, if it collides with the second body, then the first body comes to the rest and the second body moves with the velocity of the first body. So this is a important conclusion, and if suppose your m2 is very large than m1, then if m1 collides with the m2, then it will move return back with the same velocity but in opposite direction. So this is all about collision in one dimension. I have told you in one dimension. In two dimension it is nothing but here the components will come along x-axis and along y-axis. Here the components will be resolved along x-axis and y-axis. So along y-axis there will be initially no momentum, because the body is moving, initially the body is moving in one direction, and it gets split into, it moves into the two dimension. Now the another topic is the system of particles and rotational motion. So here system of particles, that means when a body is rotating, that is what is the main point is that when a body is rotating, then we consider that the body as a system of particles. When a body is rotating about a given axis, we consider it as a system of particles. And here this is system of particles. So the first point here comes out that the center of mass of a body. So in one dimensional it has been calculated, it has been taken the help of the vector, by it has taken the help of coordinate system, and by the coordinate system it has tried to explain you the center of mass. That is, we consider two bodies of mass m1 and m2, and m1 is situated at a distance x1 and m2 is situated at a distance x2. We are considering in two dimensional, that means first of all that means let us take in one dimension only, that is along x-axis we are considering two mass m1 and m2. The m1 mass is situated at a distance x1 and m2 mass is situated at a distance x2. So here the coordinate of the center of mass will be m1 x1 plus m2 x2 divided by m1 plus m2. Here, see, most important thing I want to tell you that here we are considering the center of mass. This you must remember that first of all they have considered the uh, uh, two bodies m1 and m2 along the x-axis. m1 is situated at a distance x1 and m2 is situated at a distance x2 from the origin. m1 is x1 from the origin, m2 is x2 from the origin. So here your coordinate of the center of mass x will be m1 x1 plus m2 x2 by m1 plus m2. Now if you increase it, move to three body, so again this will be m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. So here you see that for three body it moves to m1 x1 plus m2 x2 plus m3 x3 by m1 plus m2 plus m3. And if you go for four bodies, then similarly it will be m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 divided by m1 plus m2 plus m3 plus m4. So this is it is along the x-axis. Now if you consider a two-dimensional plane, so in the two-dimensional plane again the same thing will happen, but along y there will be another coordinate, y coordinate. Your x coordinate will be the same, that is m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 by m1 plus m2 plus m3 plus m4. Similarly for along y, the y coordinate of the center of mass will be m1 y1 plus m2 y2 plus m3 y3 plus m4 y4 by m1 plus m2 plus m3 plus m4. And if we consider in three dimensions, again the same effect, the coordinate of the center of mass, let us consider for four particle system, for four particles of m1 m2 m3 and m4. So the center of mass will be x center of the coordinate of the center of mass, x coordinate will be m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 divided by m1 plus m2 plus m3 plus m4. Your y coordinate of the center of mass will be m1 y1 plus m2 y2 plus m3 y3 plus m4 y4 by m1 plus m2 plus m3 plus m4. And similarly your z coordinate will be m1 z1 plus m2 z2 plus m3 z3 plus m4 z4 by m1 plus m2 plus m3 plus m4. So here for I have considered for for four particles, and if you can go for n number of particles. So now when you have considered three dimensional, so this again can be confined, this whole thing, that means the center of mass, that is in three dimensional, this whole can be confined to that means at now in three dimensional system the center of mass, let us take for four particles, that is of mass m1 m2 m3 and m4. Here your center of mass x is m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 divided by m1 plus m2 plus m3 plus m4. And your y coordinate of the center of mass is m1 y1 plus m2 y2 plus m3 y3 plus m4 y4 divided by m1 plus m2 plus m3 plus m4. And your z coordinate of the center of mass will be m1 y1 m1 z1 plus m2 z2 plus m3 z3 plus m4 z4 by m1 plus m2 plus m3 plus m4. Now this you can again confine to one piece, that if you consider the position vector, and when you consider the position vector it becomes what it becomes, that is uh, the if your center of mass is coordinates of the center of mass is x, y, z, so your position vector will be x I cap plus y j cap plus z k cap. That means you confine it to the position vector. You can confine this to the position vector. So here you see that, that means this is how they have confined it to your position vector. So this is how we find out the center of mass in 1 dimension, 2 dimension and 3 dimension, because you must remember, when a body is rotating about a fixed axis, we consider uh, it is as a system of particles, as a system of particles, and it is rotating about a fixed axis, and every particle is at some distance r from the axis. Now since we are considering the center of mass in this topic, we are considering the center of mass. Now first of all, I have shown you that this book, it has shown you how to find the center of mass of a system of 2 particles or 3 particles or 4 particles or n particles along x, along 1 dimension, along 2 dimension and along 3 dimension. How we have find the center of mass, this I have shown you for a system of particles. Now motion of the center of mass. So the motion of the center of mass, this center of mass, that means the motion of the center of mass, as we know that center of mass, it is the whole mass of the body is concentrated at the center of mass. So the whole motion of the center of mass, that means the whole body is concentrated at a point. The mass of the whole body is concentrated at a point, that is the whole body is concentrated at the center of the mass. The whole body is concentrated at a point, and that means the mass of a body. So the mass of a body and the acceleration of the center of mass. The mass, remember that mass of a body and the acceleration of the center of mass is equal to the sum of individual masses and their individual acceleration. You remember that the important point is that the mass of the body in dot acceleration, that is the acceleration of the center of mass, is equal to the sum of the product of individual masses and the individual acceleration of the whole body or the whole system. Sum, it is the sum of m1 a1. That means let us take the mass of the body m and its acceleration, center of acceleration, mass, acceleration of the center of mass. Let us take the acceleration of the center of mass as capital A and the mass of the body as capital M. So m into acceleration, that is capital A, will be equal to m1 a1 plus m2 a2 plus m3 a3 plus dot 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 plus mn an. Now here, that means ma, that will be equal to, we know that from the second law, m1 a1, that is f1 plus f2 plus f3 dot dot fn. So this is equal to m into a, that is equal to f external. Why m into a is equal to f external? Because your internal forces, that is the internal forces of the particles, because of Newton's third law, your internal forces will be 0. According to the Newton's third law, your internal forces will be equal and opposite. So here the important point is that your internal forces will be 0, only the external force will be there. So that is mass capital M into A, that will be equal to F external, that is the external force. So remember, what I want to tell you is nothing but the for a system of particle or for a body, that is a system of particles in if we first of all to explain you, it has considered one dimension along x-axis, and along x-axis your coordinate of the center of mass is, if you consider two particles, it is a m1 x1 plus m2 x2, that means m1, let us consider two particles along x-axis, m1 is situated at a distance x1 and m2 is situated at a distance x2 from the origin. So your coordinate of the center of mass will be m1 x1 plus m2 x2 by m1 plus m2. And if you consider two dimension, then your coordinate of the center of mass for two particle system will be m1 for x coordinate, that will be m1 x1 plus m2 x2 by m1 plus m2, and your y coordinate of the center of mass will be m1 y1 plus m2 y2 by m1 plus m2. And if you consider if you consider three dimension, so your z component will be m1 z1 plus m2 z2 by m1 plus m2, because we have considered only two particle system in three dimensions. So if we consider n particles, so it will be your x coordinate of the center of mass will be summation of m1 mixi, summation of mixi by summation of m, and your y component will be summation of m iyy by summation of m, and your z component will be summation of m zi by summation of m. This is the coordinate of the center of mass. So again, now it wants to explain that the acceleration of the center of mass means m into acceleration of the center of mass, that will be equal to the sum of the mass into acceleration of the individual particles. And this, if we consider the body of mass m and the acceleration of the center of mass as capital A, so m into A, that will be equal to m1 a1 plus m2 a2 plus m3 a3 plus dot 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 m and an, and this will be equal to m into A capital A, that will be equal to f1 plus f2 plus f3 dot 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 f n. And so this mass F into m, capital M into A, this will be equal to the external force, because your internal forces are equal and opposite according to Newton's third law, and it cancels out. So here they want to show that, in this book they want to show that this is also Newton's second law is also applicable to a system of particles. This is also applicable to a system of particles. So here we find that so in this it has been tried to relate, this is nothing but in this system of particles and rotational motion, here they have only tried to relate with linear velocity, they have only tried to relate you with the linear velocity. So suppose linear velocity, that is your now when a body is rotating about a fixed axis, when a body is rotating about a fixed axis, now let us consider a particle, a body is about a fixed let us consider a body, it is rotating about a fixed axis, that means the axis of the body, the rotational axis of the body is perpendicular to the axis of the body, means rotational axis is along Z is along, we have to consider three-dimensional because your rotational axis is along Z axis. Your rotational axis is along Z axis and the body is in XY plane. So your rotational axis is perpendicular to the XY plane and the body is rotating along the about the Z axis. So if we consider any point on the Z axis which is at a distance r, its position vector is r, its position vector is r. Here you find that if the body is rotating in anti-clockwise direction, if the body is rotating in anti-clockwise direction, if the body is rotating, means if this body is rotating in xy plane, that means your body is rotating in xy plane. Remember this, I am telling it again. That is, let us consider a body which is in xy plane and its axis of rotation is along the z axis. If we consider a particle of that body is rotating in an xy plane and the particle is at a position vector r from the origin, it is at a position vector r, and when the body is rotating in anti-clockwise direction, your in anti-clockwise direction, here you know the relation between V and R, you know the relation between V and R, that is V is equal to here r omega, but here this will be, here you see r omega, but one thing you remember here, because we are considering it in vector, here you see that the particle's position vector is r and the body is revolving in anti-clockwise direction. So your velocity vector will be perpendicular to the position vector, your velocity vector will be perpendicular to the position vector, and the direction of the velocity were perpendicular to the position vector, and the direction of the angular velocity will be upward, the along the z axis upward. Your direction of the angular velocity will be directed upward. So here your v is equal to v vector, that is equal to omega cross r, angular velocity cross position vector, your v vector. That means you remember one thing, that is, if you can, means I have considered this, the body is in xy plane and your z axis, it is the perpendicular to the xy plane. Now we consider a point, a particle m1, and which is at a position vector r1. So the body is moving in anti-clockwise direction. Your velocity vector will be perpendicular to the position vector and the body is moving in anti-clockwise direction. Here your angular velocity will be directed along z axis, will be directed along the z axis. So if it is moving in clockwise direction, if it is moving in anti-clockwise direction, if it is moving in clockwise direction, it will be the direction of omega will be the towards the negative z axis. So v vector is equal to omega vector cross r vector. So it has given a relation between angular velocity and linear velocity in terms of vector. They have given you the in terms of vector, and they have shown you that if your linear velocity is in the direction, in the anti-clockwise direction, because the linear velocity is always perpendicular to the position vector, and if your linear velocity direction is along the anti-clockwise direction, so your angular velocity will be along the z axis direction, and if it is in clockwise direction, your angular velocity direction will be in the negative z direction, and your v vector is equal to omega vector cross r vector. Now again here they have given that is the moment of a force torque. Now here torque, that is rotational effect, the rotational effect of a body, the rotational effect of a body is created by the by torque. That means two opposite forces must act in opposite direction, or that is called moment of a force, and forms a couple. But here that means rotational effect, that means in linear motion your external force, that is your external force, it acts linearly on a body and the body moves in the linear direction. But when there is a rotational motion, that the rotational motion is created by the torque, and that torque is equal to r position vector cross f vector. That torque is equal to the position vector r vector cross f vector, and this f vector always acts, it is considered always it acts perpendicular to the position vector. It's always it is considered perpendicular to the, for torque this force is always considered perpendicular to the position vector. So here your torque is equal to r vector cross f vector. Now now they have related this, because when there is here you see in linear motion, as there is a linear momentum, that is mv, similarly there is angular momentum. Remember all this, that as there is linear momentum m into v, similarly there is angular momentum, and this angular momentum is equal to r vector position vector cross p vector, that is the momentum vector, that is r vector cross p vector, and your p vector is your linear momentum. So these are the formulas you must remember, that is your angular momentum, these are all vectors. Your angular momentum is equal to the position vector r vector cross linear momentum p vector. So here it has another important point is that your change in angular momentum, your change in angular momentum is equal to torque. Here see the relations. Your change in angular momentum of a particle, change in angular momentum of a particle means that this particle is is rotating about a fixed axis, that means moving in a fixed revolving or rotating in a fixed axis. So here you see that the change in angular momentum is equal to torque. Similarly in linear you have seen that change in momentum, change in rate of change in momentum, that is in angular momentum also, in case of angular momentum, in angular motion, not let us state that in case of angular motion, your rate of change of angular momentum, that is your rate of change of angular momentum, that is angular momentum is represented by L. So dl by dt, that is equal to rate of change of angle, that is equal to torque. And in your linear motion, here you see that the rate of change of momentum is equal to force. So in this chapter it is nothing about it, they are trying to explain you the relations between the angular motions and linear motions. So here you see that rate of change of, that means at first in this book, at first they try to describe for a particle and then for a system of particles. For a particle, they told you that the rate of change of momentum of a particle, for a particle, they first of all consider particle, that is equal to the torque. Now they consider the system of particles and the same rate of change of momentum for this system of particles is equal to the torque external. This is also equal to the torque external. Now we come to the moment of inertia. So we come here to the moment of inertia. So this moment of inertia, in this moment of inertia, it is analog, this moment of inertia is analog to the mass of a body, and this moment of inertia is a summation of m into r square. Suppose a body consisting of m1 n numbers of particles, and their distance from the axis of rotation, are r1, r2, r3 dot to rn. So the moment of inertia of this body I is equal to summation of mi into ri square. That means this moment of inertia is analog to your it is analog to your mass in case of linear motion. So here this is now it has been related with here you see that torque, that is you in linear motion we find that F is equal to mass into acceleration. In linear motion you have found that F is equal to mass into acceleration. Similarly, in angular circular motion, that is in circular motion, your torque will be equal to moment of inertia into angular acceleration. Your torque will be equal to moment of inertia into angular acceleration. So remember here the formulas which are most important for a particle, that is dl by dt is equal to torque. For a system of particles, d capital L momentum of total momentum of the system of particles by dt is equal to torque external. Your torque is equal to r cross f, and your angular momentum, that is equal to r cross linear momentum, and your torque is equal to moment of inertia into angular acceleration. This is all about your rotational system of particles and rotational motion. That is, here only the thing it is you must remember that when a body is rotating, then we must consider the moment of inertia. Instead of mass, we consider moment of inertia. Now your last topic is gravitation. Now my last topic is gravitation. So here Kepler, he introduces three laws. That is, we actually consider the orbit as circular orbit. That is we consider it as a circular orbit. The planets are moving around the circle in a circular orbit. But Laplace, this Kepler stated that these are not circular orbits, but they are elliptical orbits, and Sun is located at the focus. So all this ellipse and focus you will study in class 11 in maths book. It is given here in the book. That is an ellipse. It has two focus and two vertices. You will learn about it, but for today, the Kepler stated that the orbits which we originally, it was stated that the orbits are circular, but it is actually, according to Kepler, it is elliptical, and sun is located at the focus. And the second law, it was that the area sweeps away, that the sun sweeps away area in equal interval of time. The line that joins any plane to the sun sweeps equal areas in equal interval of time. That is, the sun, it sweeps away equal area in equal interval of time. This was the second law. And your third law was that the square of the time period, your square of the time period, it is equal to cube of the major axis, cube of the major axis. And Newton's third law states that the square of the time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse. That means the square, the third law, it states the square of the time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. The semi-major axis, that's also you will learn in your maths. It is everything, it is given in your class 11 maths in conic section. In ellipse it has been discussed in details. So here your time period of evolution t square is equal to is proportional to a cube. A cube, it is the semi-major axis. Major axis, the axis in which the focus lie, is called the major axis. So t square is proportional to a cube. So these three laws were stated by the Kepler's. One, for the first law, I am repeating it. The first law, it states that the orbits are elliptical orbits and sun is located at the focus. And the second law, it states that the line that join any plane to the sun, the line that join any plane to the sun, the line that joins any plane to the sun sweeps equal area in equal interval of time. That means the sun sweeps out equal area in equal interval of time. And the third law, it is that the square of the time period of revolution is proportional to your semi-major axis, cube of the semi-major axis. Square of the time period of revolution is of any planet is proportional to the cube root of semi-major axis. Cube root, not cube, a cube, not cube root, cube, a cube. That is, t square is proportional to a cube. Now, Newton's universal law of gravitation, that you have already studied in your class 10, that is in any two body in this universe there is force of attraction, and this force is proportional to the product of the two masses and inversely proportional to the square of the distance between the two. So F is proportional to m1 into m2 by r square. This you have already learnt in class 10, universal law of gravitation, Newton's universal law of gravitation. So F is equal to capital G m1 into m2 by r square. G is called the universal gas constant, universal constant. um that is F is equal to capital G m1 into m2 by r square, where G it is the universal constant, gravitational constant. This is the universal gravitational constant. Now this universal gravitational constant is related with acceleration due to gravity. That means if F is equal to capital G m into, let us take a body of mass, let us relate it with the mass of the earth, let us relate it with the mass of the earth, that is m be the capital M be the mass of the earth, and another body of mass m, and which is at a distance r it is the radius of the earth. That means it is on the surface, or anything above the earth's surface will be considered as r, because that height is negligible in comparison to the radius of the earth. So F is equal to capital G into small m into capital M by r square, where capital M is the mass of the earth and r square is the r square is the radius of the earth. So this will be equal to mg, that is the weight of the body, mg. So mm cancels out, so your g will be equal to capital G into m by r square. So this is the relation between small acceleration due to gravity and universal gravitational constant. Now my last topic is that how the gravity varies with altitudes, and varies with your gravity varies with altitude and with depth. So here the formula is that gravity at any height, gravity acceleration due to gravity, the acceleration due to gravity at any height is equal to acceleration due to gravity into bracket 1 minus 2h small letter h by capital R, that is the radius of the earth, small h that is the body which is kept at a height h from the earth's surface. So again I am telling the formula. The acceleration due to gravity at any height h is equal to the acceleration due to gravity g bracket 1 minus 2h by small letter h by capital R, where h is the height at which the body is kept from the surface of the earth. So here we find that as the height increases, your acceleration due to gravity decreases. So the acceleration due to gravity is less on the surface of the mountain. And similarly with depth, the formula for depth is that the acceleration due to gravity at any depth, that is below the surface of the earth, is equal to g bracket 1 minus d by r, where d is the small d is the depth and r is the radius. So here again your with the increase in depth, your acceleration due to gravity decreases. The acceleration due to gravity is maximum at the surface of the maximum at the surface of the earth. Now the last topic is the gravitational potential energy, and this gravitational potential energy is equal to minus capital G into capital M, that is mass of the earth, and small m, that is the mass of a body, and by small r, that is the mass of the small body m, it is kept at a distance r from the surface of the earth. So here your potential energy is equal to minus G capital M into small m by r and small r, and the sign is negative because the potential energy is due to the gravitational attraction between the earth and the body. Here you see the, because the potential energy is negative because of the gravitational attraction between the earth and the surface of the body. So this is and here this work in gravitational potential, and the work this potential energy is derived when to bring a body from infinity to the point r, that means r, it is the distance from the surface of the earth, the work done, and this potential energy is equal to minus capital G m capital M into small m by r small r, where capital M is the mass of the earth, small m is the mass of the body, r it is the distance from the body, which distance of the body from the surface of the earth. So this is all about your first book, and there are others, escape velocity and orbital velocity. They are just the velocities which is not there is nothing about it. So this is all about in your first book. This is the revision I have done it for class 11.